Welcome to Module 3 on the Milton-Madison's Design, Build, Bidding, Accelerated Bridge Construction, and Maintenance of Traffic. We're pleased to introduce our speaker, Travis Butz. Travis is a senior engineer in the Bridge and Structural Design section of Burgess and Niple's Columbus, Ohio office. He was the lead designer of the river piers for the Milton-Madison project and served as part of the design team for the temporary and permanent approach spans and the Span D bridge slide. Travis?
Thanks, Mary Lou. So in this module, I'm going to cover the bidding process, how we used accelerated construction methods, and that played a part in our team winning the job. And I'm going to go through our plan for sequencing the construction to maintain traffic during the project. This is just going to be a general overview of how everything went together, and in later sections we're going to cover in more detail the engineering that was involved. So I'm going to briefly review some of the things that have been covered in earlier presentations, just to set the stage for what we did. The project came out in 2012, and as has already been discussed, it was going to be a design-build project. We were going to replace the bridge on the same alignment as the existing bridge, and because this was a truss, we couldn't use part width construction to maintain traffic, so the bridge was going to need to be closed for a pretty significant period of time while the new superstructure was constructed. And the bid documents called for a new truss superstructure that was going to be substantially wider than the existing bridge, and we were also going to strengthen and widen the piers. And you can see the difference between the existing pier size and the proposed in this rendering. And a large part of that strengthening could take place while the existing bridge was under traffic, but we still need a substantial closure time to replace the superstructure. So the bid documents called for the contractor to construct and operate a ferry service during the period where the bridge was going to be closed, and this was anticipated it would be about a 1-year closure to replace the superstructure, so you'd have a pretty long operation period for that ferry. See that you would need some sort of ferry boat. This was what our initial idea of what that boat might look like on the lower left, and you would also need to construct facilities, docks and unloading and loading areas at each end of the bridge. So that was going to be a pretty substantial cost to maintain that ferry. And the contract documents called for 240 vehicles per hour to be moved by that ferry. And you know, as we considered this and thought about that number, that's a huge number of vehicles to move across the river. And when you think of that number and look at that boat, you're thinking it's going to be difficult to pull that off. So we brought in an expert in the area and came to the conclusion that we were going to need a bigger boat to make this happen. So with that 240 vehicles per hour, we were probably not looking at a boat of this size. It was going to be a boat more like this. And that boat means more money to operate, more money to construct the docks, more money to construct the loading areas, and all that considered, it made finding an alternative to the ferry service a pretty attractive alternative. So the bid was constructed in an A plus B formula, where A is the actual cost of construction for the boat, including for the bridge, and that includes the cost of maintaining that ferry. And the B is some sort of factor that converts the proposed construction schedule into an equivalent cost. So in this case, the B factor was the number of closure days times $25,000 per day. And if you're considering a year closure, that was going to amount to a little over $9 million. So if we could find a way to reduce that closure time down to just a few days, that was going to give us an extra $9 million to play with to bring about our reduced construction schedule. So with that considered, we put our heads together and we came up with the idea of constructing the new bridge on a parallel alignment to the existing bridge, just adjacent to it, and maintain traffic on the existing bridge while we did that. And this was going to allow us to limit the bridge to just a few days of closure and eliminate the need for the ferry service entirely. And we were able to have some preliminary meetings with NDOT prior to the bid and get some buy-in on this concept, so we knew it was going to be an acceptable alternative to the original proposal. So before the bid, we had to dig in and determine how we were going to carry this process out. And we had to have an accurate enough picture of all the temporary structures that were going to be involved in order to estimate both our design effort to produce this and also what we were going to need as far as construction quantities and in order to construct what we were proposing. And given how unique a thing we were proposing, this was a pretty involved process, and it was difficult to pull off prior to the bid. But in the end, we submitted, and we're one of 5 teams. Our bid for the construction cost was $103 million with a 10-day closure. And as was already mentioned, all the other teams bid in the neighborhood of a year closure. So the A part of our bid was not the low bid. Our construction cost was not the lowest, but because of that 10-day closure period, that we were able to win the job. So the next few slides are going to walk through what we were proposing as far as the construction sequence of the bridge. And these show the order of how things were built and demolished, and how we were able to maintain traffic throughout construction. So in this first picture, the Kentucky side is the near side, the Indiana side is the far side. In the first step, we're constructing, while we're still maintaining traffic on the existing approach and the existing bridge, temporary ramps approaching from the side of the existing bridge. So that's done entirely offline. And the next phase, this is the first, our sequence called for 2 5-day closures of the bridge. And this is the first of those 2 5-day closures. So during this phase, we're demolishing the near approach spans for the existing truss and constructing tie-in ramps that connect those previously constructed approaches to the main span of the bridge. So we close for 5 days, do that demolition, that construction, and now we're again maintaining traffic on the existing truss and these new temporary approaches. In this phase, we're now able to remove the remainder of the existing approaches, still maintaining traffic on the existing bridge. We're now constructing temporary supports that are going to hold the new bridge on its temporary alignment adjacent to the existing bridge. And we're also at this phase starting the construction of the pier strengthening out in the river. Now a lot of time has now passed between the previous phase and this phase, but we have now constructed the new permanent approach that's in line with the existing bridge, and we've constructed the main truss spans and 1 approach span adjacent to the existing bridge. And you can see at this point those 2 things are not tied together, so there's no access to this the new bridge in its temporary position. But also during this period, we're still maintaining traffic on the existing bridge and on the temporary approaches. And now we're constructing what we call the tie-in structures. So we're linking these new permanent approaches to the new bridge in its temporary position. So you come up the approach, cut over to the new bridge, on both sides of the bridge. And we're now switching traffic over from the temporary approach to the new permanent approach, and switching traffic from the old truss to the new truss. So at this point, we no longer need the existing truss, so we can remove it from service and now progress with our pier strengthening. So now you can see the pier caps in place on the strengthened existing piers in the river. And again, we're still maintaining traffic on the new truss in its temporary position. And finally, now we can slide the main span and the end approach span over to the permanent position. And this is the second 5-day closure. So we close the bridge for 5 days, perform that slide, and link everything together. And once that is done, we can now open the bridge in its permanent position to traffic. And this is a shot of the temporary approaches on the Indiana side. And these were constructed using rolled steel sections supported on steel pile bends. The driving surface, which is under construction here, is made of timber crane mats with asphalt installed on top of them, and we've got portable concrete barrier acting as barriers. This picture was taken during the first 5-day closure, so you can see the existing approach spans demolished here in the background, and the link between this temporary approach and the existing truss is under construction in this picture. The temporary approaches were designed for 75% of HL93, which is modern highway loading, which is considerably more than the existing truss was good for. This is another view of that Indiana approach. This time you can see the new approach spans under construction. So the existing spans are gone. We're now constructing new pre-stressed I-beam approaches. And you can also see the piling for what will be the tie-in structure. So the new truss will be constructed on this alignment, and it'll get tied to the new approach span temporarily with the tie-in structure here. And this is the Kentucky temporary approach under construction. And this is, again, during the 5-day closure period where we're tying in the temporary approaches to the existing truss. So you can see the partially demolished existing approach here on the right, and you can see the installation of crane mats and beams going on as part of this tie-in structure here. This is a shot of the completed Kentucky approach. You can see that the temporary approach here tied in now to the existing truss. And this is the new permanent approach under construction. So the beams are in place, the deck's not yet poured. And you can see here the end of the new truss in the temporary position, and also this is called span D. It's the end approach span that's also under construction. And this is the approach span that is going to get slid over with the truss at the end of construction. And you can see here the tie-in structure also under construction. And this is a triangular bridge that's going to link the new permanent approach to the span D in its temporary position. So that's going to be the second phase of MOT. And this is the shot of the Kentucky approach just before traffic was switched from the existing bridge to the new bridge. So you can still see traffic running on that existing truss. You can see here the new approach, mostly constructed, and the tie-in structures with the deck in place, and then the new truss with the deck in place. So we just need to add some barrier here, and this will soon open to traffic across the new bridge in the temporary position. This also gives you a good picture of how much larger the new truss is relative to the old truss as far as width. So moving on to the pier retrofits, throughout those stages of maintaining traffic, we're also stepping through the process of pier strengthening. And I'm going to touch on this just briefly here. The entire next presentation will be about this process in detail. But just to give you a quick overview, this covers, again, the reasons we need to strengthen those piers. We're putting this newer, larger truss in place on top of those existing piers. The existing caissons are unreinforced, so we needed to add rebar down there to strengthen them. We also need to strengthen the stem and put on a wider cap to accept that wider truss on top. And these are a few photos of how the strengthening was carried out. Everything you see here was done while we were still maintaining traffic on the existing bridge. Constructing a cofferdam around the piers, dewater, and as Aaron discussed, we're coring holes into the existing caisson and installing bundled rebar down those holes and grouting it into place. So you can see a shot there in the upper middle of piles of core holes that have been extracted as the coring took place, and the coring in operation up there in the upper right. Those cores go down between 40 and 70 feet into those caissons. And then once that caisson reinforcement is installed, we're moving up. So on the left side there, you can see the beginnings of the stem encasements being poured. So that's constructed up from the top of the caisson up to the lower portion of the pier cap. And all that is built prior to moving traffic over to the new bridge. So this slide walks through the construction sequence of the main spans and shows how the pier strengthening fits in with that. So we're starting here with the pier encasement is now constructed up to the bottom of the pier cap around the existing pier. And we're still now maintaining traffic on that existing bridge. And moving forward, we bring in the new truss, lift it into position, bring in what's called the sliding girder, which connects the temporary pier tower over to the existing pier encasement, and also supports the truss in its temporary position. So we're dropping that pier down. And at this point, we can now remove that existing truss, construct the new pier cap, and slide that truss over into position. At which point we can remove all that temporary material and open up the bridge to traffic. So as we discussed earlier, aside from the main truss slide, I'm sorry, this is so here you can see the temporary pier in place. You can see the sliding girder linking the temporary pier tower over to the what's called the sliding girder pedestal mounted on top of that pier encasement, supporting the truss in its temporary position. So we're constructing these temporary piers and sliding girders at each of the main river piers, supporting the truss. And there's a huge amount of engineering that went into this, and that's going to be discussed in detail in a couple presentations from now by Murray Johnson of Buckland & Taylor. So aside from that main truss slide, we're also sliding the end approach span, which is span D. And this is on the Kentucky side, it's the span adjacent to the new truss. And the next few slides are going to walk through how that slide was carried out. So this is a review of how that slide fits into the MOT sequence. Span D is constructed offline with the truss, and it picks up traffic once traffic is switched over to the main truss through the tie-in span, which is the triangular section constructed right here. So during the same period we slide the truss over, we're also sliding span D over. And this was our plan of how to do that. So span D is a relatively normal pre-stressed I-beam bridge, except that we have a little bit larger than normal in the diaphragm here, and we've got embedded in that a conduit designed to allow pulling strands to pass through that diaphragm. So we've got one of these at each end of that bridge. In its temporary position, the bridge rests on a temporary steel bent, and it's going to get pulled over to a permanent concrete bent in the final position. And mounted on that bent, we have a jack stand and a hydraulic strand jack that we're going to use to pull the bridge over. So the strands pass through that conduit. They're anchored on the backside of the diaphragm, and we're mounting that. It's temporary. In its temporary position, it's on elastomeric bearings. Prior to the slide, we're going to jack the span up, install sliding bearings, and slide this over on a stainless steel surface to its permanent position. So the next few slides are a graphic of how that slide works. So you can see here the black squares represent the elastomeric bearings in the temporary position. So this is the temporary pier cap. We're going to lift that span up at both ends, remove those elastomeric bearings, install the temporary sliding bearings, lower the bridge back down on those bearings, remove the jacks, install our strands, and pull the bridge over to its permanent position. Now, during the pulling process, we have a bumper over at the jack side because we're equipped to pull the bridge over to its new position. We are not equipped to push it back in any way, so it's important that it not go too far. And at this point, we can install the jacks again, lift the bridge up, take out the sliding bearings. We're reinstalling the same set of elastomeric bearings. And lowering the bridge back down onto those bearings. And the jacks are out, and we're ready to put traffic on it. So we have a few slides here showing photos from that bridge slide. And this one, you are looking at the permanent pier set up to receive the span, and you can see the sliding surface there. It's a stainless steel surface. It's been lubricated before the slide, and over top of that you can see the strands and the strand jack there at the end of the pier that's going to pull the bridge over. So you're looking at the new permanent approach spans on the right side there, and they're set up. After the slide, we're going to connect span D to those approach spans with a link slab, which is just a slab that passes over the ends of those I-beams and connects the two spans together. And this is a shot after the slide. So we're now standing on the temporary pier looking at the sliding surface there at the bottom left. And you can see the end of the new truss on the top left. It's still in its temporary position. And span D there to the right, now moved over to the permanent position. So this is a time-lapse video of the bridge slide. You can see here, hopefully this is coming through all right. It may be a bit choppy, but you can see the strand jacks over to the right. The slide's getting controlled from the up on the bridge. This guy in the orange coat is managing it here from a control center. He's got the pumps for the jacks up here on the span. And here it is from a different angle on the ground. You see those jacks operating on both ends of the bridge, pulling both ends simultaneously. So we're monitoring to make sure that both ends of the bridge were moving at the same rate. And this process took between 1 and 2 hours to carry out. So it went relatively quickly, especially compared to the main truss slide. So a few lessons learned from this process. First of all, the A plus B bidding worked as designed, I think, in this case. It was a great tool to encourage the bidders to innovate. And without having that time incentive as part of the bid, it probably would have resulted in the bridge being closed for a year and everybody using a ferry boat over that period of time. That said, what we proposed ended up being really complicated, and which we knew going in, but it presented a lot of challenges both in design and construction. And you know, we couldn't anticipate everything that was going to happen. We did the best we could, but there's always the unexpected. And finally, it may be an obvious statement, but sliding the small bridge is much easier than sliding the big bridge. There was a lot of sliding span D wasn't easy. A lot of thought and planning went into that. It ended up going very smoothly. With the main spans, there are a lot more considerations as far as having multiple interior supports there to keep moving simultaneously over a much longer distance, having a much more flexible bridge, and having a bridge that's much more exposed to wind to make that process much more complex. And then you're going to hear a lot more about that in Murray's presentation later on. So with that, I will open it up to questions. I also want to acknowledge a lot of the material in this presentation came from sources Walsh Construction, and Charlie Gannon in particular provided a lot of the photos I used. I used a lot of Michael Baker and Buckland & Taylor's graphics in this presentation, and also Deborah Crawford, who manages the Facebook page, used several of her pictures as well.
Okay, thank you. Thank you very much, Travis. This is an amazing project. We'll now begin the Q&A session. We've received several questions. One that just came in is, did you consider the alternative to slide the existing bridge first, then construct the new bridge at the final location? And if so, what is the different outcome of these two alternatives?
I don't think that option was ever seriously considered because of the condition of the existing bridge. I don't think that we knew that it could survive distress from a slide. It definitely was not designed for that. So I think that was the reason we decided to go the way we went with sliding the new bridge.
Okay, thank you. And then you constructed several temporary structures in order to maintain traffic during construction. How much design work did you do pre-bid in order to estimate bid quantities for these structures?
It's an interesting question. We as much as we thought we needed to come up with an accurate price, which is, you know, with the amount of you know, the huge number of structures over there, we had to make a lot of assumptions in that process, and we tried to be as conservative as we could in those designs without investing a huge amount of time in design, just as far as both estimating what our effort was going to be during construction and estimating quantities for Walsh's use to estimate the cost of those structures.
Okay, thank you. And then it looks like this is the last question. How were the timber crane mats on the temporary approach structures attached to the steel beams?
that was a big concern during design because you could see those temporary approaches were on a pretty significant grade, so we had braking forces to deal with traffic on those crane mats, and we were setting timber on top of steel, so there was a big potential for those to slide around. So we used steel anchor bolts and clamps to clamp those things securely to those beams to make sure they weren't going to move around as they carried traffic, and that seemed to work pretty well.
Okay, thank you. We have no more questions, so we're now at the end of the third 40-minute module. Thanks again to Travis Butz and to all those who participated in the third module.